Hey folks, got a really quick tutorial for you here, hopefully quick. Anyway, I've been seeing this effect popping up on Twitter and I just figured that seems like a perfect use case for simulation nodes, just to kind of play around with it. Great little learning exercise, and while this might not be the most optimized workflow, should still give you a nice little intuitive understanding of how the system works, how we can work with named attributes, and just generally having a bit of fun. If you're interested in more simulation node stuff, then you can check out the rest of my courses over on the nodegroup.xyz website, linked down below. So let's jump in. What are we building? Well, it's a very simple loop, and it really just starts with making a couple of points, creating your grid with the score system in the background, and this can be customized as well. So at the moment we have 10 by 10 for 100 points, and we can go up to something like let's do something a bit bigger. Let's go up to 31 by 31. So now we've got 900 points. So the scoring is going to be a little bit slower on this one, but the shape is going to be more interesting. And essentially it's a very customizable experience here. So let's jump in properly. Okay, I've got Blender 4.1 here, but you can do this with 4.0, I believe. There's nothing special that we're using. Create yourself a new object. You don't need any collections. And just rename this object game. I'm going to create a new geometry nodes object here. And again, I'm just going to rename this node graph to game. Now, before we collapse that side, actually, I will just change my render engine to Eevee. Turn off viewport denoising, just because that's going to cause a little bit of, it's going to cause some artifacting, some ghosting. I'm going to be doing all of my shaders just with emissive. So I'm also going to turn off ambient occlusion and screen space reflections, just everything I can to speed this up for you. Frame rate, I'll leave at 30 FPS for me, and I'm going to make sure that my frame range doesn't just go to 20 to 250, because that's only 8 seconds of gameplay. I want to be able to watch this indefinitely, so I'm just going to add a bunch of zeros to the end there just to get the max frame count. So in our geometry nodes, first of all, we want 2 points. So I'm going to add a points node, and let's just connect this straight to the output. That was Shift-Alt left mouse button. Let's increase our radius to 1 meter. And we're going to be setting our positions just to begin with. So I want to have -10 and +10 as my start positions. So to do this nice and easy, I'll use a switch node. So just dragged that search to give me options and then type switch. And I'm going to be switching using the index, which is going to give me a 0 and a 1 because I have 2 points. There we go, count of 2. And that means that I'm basically using this as a Boolean. So now I can move one of my points to the left and one of my points to the right. Doesn't really matter where you put them. I'm going to go for -10 and 10. And my play zone is going to be in this sort of 40 meter square area. We're also going to be making sure that we store a named attribute for ourselves based on the original indices. So store an integer on the point domain based on that original index, and I'm just going to call this IDX. Now, when we're working with simulation, we want to just add the simulation zone, and this is going to give us a per frame update. And the way that simulation works is during frame 0, or frame 1 in this case as the first frame of the timeline, information is stored in the simulation input node. It then runs through and you can read the output. And then on the following frame, so frame 2 and beyond, it's simply going to load the data from inside the loop. So anything you do before the loop is only going to be changeable on that first frame. Any changes that you make after that first frame are not going to be updated because the loop is then closed. It's just looking at the information it already has. First thing, nice and easy for us to do here, let's use a set position node to move our points. Now, where are we moving them to? Well, we want to give our points a random direction and potentially a random speed, depending on how you want to play this. Let's add another store named attribute node. This time we're going to be storing a vector. I'm going to call it move. It's not the speed, it's not the velocity, it is the displacement that we're carrying out each frame. So move is fairly descriptive there. And I'm going to use a random value a vector between -1, -1, 0, and 1, 1, 0. So you can see this is just going in the XY plane. Now you can quite easily extend this game to be three-dimensional. That might be something that you want to do. But for us, we're going to keep it simple. We're going to work just with the XY plane here. And rather than having any vector, you know, it could be like this, it could be like this. I want them to have the same length, so everything moves at the same speed. Everything is predictable. And to do this, we're just going to take the direction of the vector by normalizing it. When we normalize a vector, we make its length equal to 1, so it becomes a unit vector. And then to control the speed ourselves, we're going to use a scale node, which is again a vector math, and then that goes into our store named attribute. So this scale value, this value here, this is the distance per frame that you're traveling. Now, back in our loop, we can set the offset to be the named attribute move. Now, if I just play the timeline, you can see that our points then just start shooting off into space. This is exactly what we want. The next thing we need to do is actually deal with collisions. But for us to deal with collisions, we need a collider object. Let's start building our base grid. Select these point nodes, Control J, F2, to put them into a frame and rename it. This one is create points. And I will just move this up. Also, I like to do this with my simulation and repeat zones. Grab your simulation input, go to the node tab, and just make sure you're naming your inputs properly. This is points, and I'm going to add a new one for grid. This is our background grid. Back down to the bottom. So before our loop again, we're going to create this grid. Add a grid node. This is going to be 40 by 40 to give us this nice big space. And the number of vertices are going to be 11 by 11. Why 11 by 11? Because it gives us 10 faces. If you think about how many vertices are on two faces, you have 1, 2, 3 vertices for 2 faces. So if we want a 10 by 10 grid, then we need 1 additional vertex. On this, we want to store a named attribute for the score. And the score is simply going to be a Boolean. So each tile is going to know whether it is on or off. So nice and simple. And we want a start state, which is just 50% split down the middle. So let's take our UV map, separate X, Y, Z, and we're going to take the X value here when it is less than 0.5, and that will be our initial score. Make sure that we're storing this on the face domain, and let's just use a named attribute to see what we've done. Have a look at this. So this is our start state. We have 50% on, 50% off, and each side is simply going to fight over whether it's turning on or off tiles. And just like before, we're going to be creating an index which is stable, that we can rely on using later. So this is going to be IDX, but this time rather than points, we're going to be storing it on the face domain. And there we go. This, Control J, F2, this one is create grid. Plug this up into your simulation loop, and we can start simulating. So before we can actually do any collisions, we need to split our grid into an onside and offside and create a bunch of objects to actually hit. We're working in 3D space, and I'm sure there are better ways of doing this, but the way that I've found that is very easy to set up and intuitive because we already understand working in 3D is simply to instance cubes on our faces. And then we can hit the cube and we can find information about the cubes on collision. So let's do this. We're going to take our grid, I'm going to put it into a reroute node, and I'm going to press Control G to put this into a group. Tab back out, and this group is going to be called period create collider. Why did I add the period? That was just a right click, show hide, node options to get rid of that input there. So why did I call it period create input, create collider? Well, if I go to my group drop down, you can see I don't have any groups. If I change that to just be create collider with no period, then I go to my group, you can see it shows up. So Blender has this neat little function where if you start the name of an object or the name of a data block, so whether that's images, textures, node groups, objects, meshes, whatever it is, if you start it with a period, it will not show up in lists. And that's very useful if you're creating one-off objects like this group. So we're never going to use it again, so there's no point in it coming up in our menu. So create collider, let's come in here. We've got our collider as the output, and we have our grid as the input. We're going to be creating two colliders. One is going to be the sort of the boundary that we're going to be colliding into, and then one is going to be the actual bounds around the outside that we want to stay within. First of all, let's take a mesh to points node on our grid, and let's view this. So we have all of these points where our faces are going to be. So let's change this to faces. And we're going to simply instance on points a cube. And that's pretty much it. Let's realize this so that we have actual geometry to work with, and we will pass this out as the collider. Now, clearly there's some spaces in here, and we don't want spaces. So we need to find out how big our grid squares are and make sure that our cube is that size. Actually, fairly straightforward. So let's take our grid, and we're going to separate geometry. We're going to be separating faces. And if I do it by index, then we have 0, 1, 2, 3, 4, 5, up to 100, or actually up to 99 in this case. And when we use this as a Boolean, an on-off value, then 0 comes through as false, and 1 and everything else comes through as true. So you can see that our selection for the faces is everything except from the first square, and the inversion is just the first square. So you can use separate geometry just using the index as a neat little hack to get that info quickly. Now I've got this. Let's put it through a bounding box node. And I just want to find the size of it to make sure that our cube is about the same size, or exactly the same size. So we're going to find the difference between max and min, take max, subtract min. Now if I plug this into the size of my cube and have a look at the cube, you can see that we have this absolutely flat. So we also need to add something to the z-axis. So I'll just add 2 and that'll be fine, because we're working in the xy plane. So even if I made this incredibly thin, we're still going to be bouncing off that edge that is exactly on the plane. But just because it makes me more confident in the maths, I'm going to make it a bit taller. So there we go. That is our grid here. And if I look at my named attribute score, you can see that all of these, because they're instanced on the faces, and we are storing the score on the face domain, this is all coming through nicely. So we still know what our score is. Now we also need to know what the bounds of this space is going to be. So let's grab another group input here. And we'll take this top section, Control J, make sure you're staying organized. F2, this one is create collider, or yeah, create grid collider. And this lower section, we're going to be just finding the outside loop. So let's separate geometry again. And we're just looking for the outer loop of edges. So what information do you know about an edge that would tell us whether it's the boundary or if it's internal, if it's a manifold edge? So let's grab our edge neighbors node, and this can tell us the face count. So each one of these edges has a face count associated with it. If it is on the edge, the face count will be equal to 1. So any interior faces will have 2 faces attached to them, and the outer ones only have one face attached to them. So that's how you find a boundary loop. Let's just do a standard mesh to curve and then curve to mesh. Now you could have just extruded these up and then moved the whole thing down so you're intersecting that plane. Really makes no difference in this case. We just want faces to collide with. So curve to mesh. I'm going to be using a curve line, and this needs to be going in the y-axis from -1 to 1. There we go. So just 0, -1, 0 to 0, 1, 0. And now I have a bunch of faces to hit. Just go ahead and select these, Control J, and create bounds. Let's get rid of that viewer. Rather than just joining these two things together, I'm going to join this up to my group output, and I'm going to call this second one bounds. Okay, right click, show hide node options. There we go. This is our nice little group that is going to give us all the information we need for changing how our points move, because right now they just go infinitely into space. After our set position, draw a reroute with shift right click and drag, Control G to put it into a group, tab back out. This one is going to be period. I'm only going to use it once, so let's hide it from our list. Reflect underscore move underscore on underscore hit. Reflect move on hit. Right click, show hide, node options. Tab in, make sure that we're calling these their proper names. So we have points in and points out. And we also need to be adding inputs for our colliders and our bounds. And these are both going to be geometry inputs. Tab back out and we'll just join these up. Here we go. Let's do this just simply here. So I've got my points. I'm going to separate them, so I'm just doing them one by one. Separate geometry by the named attribute. And we're going to be using the IDX attribute. So now you can see that we have 1 point on each side of that. Separate. Let's take another group input and another separate geometry and another named attribute actually. So all three of these. And we're going to be picking between colliders now. So let's have a look at this. We are going to be doing not index, but score. Now, because we're going to be doing the same thing between the point and this side of the score and the other point and that side of the score, we're going to do this again in another group just so I can use the same group twice. It makes it a little bit easier to work with and keeps your noodles a bit neater rather than just having the same nodes duplicated all over the place. So take your points. Again, I'm going to shift right click to create a reroute, Control G, tab back out. This one is going to be called period reflect underscore move. Right click, show hide, node options, tab in. Again, make sure you're calling everything properly. So we've got points in, points out. And we're also going to have our collider in as well, which is a geometry. And make sure that you're using the correct point to the correct colliders. So you want it to be the opposite side. So each point will then bounce off the outside rather than being in the middle of a big group of those tiles. So let's tab in. What do we want to do in here? We need to change the move attribute. So let's take a store named attribute. We're going to be storing move, which is a vector on the point domain. And it's going to be some modification of the existing move. And what it will be is a reflection of that vector around the collision normal. So whenever we hit a wall, whatever angle we come in at, we need to leave at the same angle. Everything is on the grid here, so it's very easy for us to just say, well, just reflect around the hit normal, and we'll just have that. It's actually very easy for us to set this up as well. So I'll take another group input out to the left here. We're going to use our collider as a raycast target. And we only want to update the move during a collision. And all it's going to be is the named attribute move, which is a vector. being reflected around the hit normal. And that's it. You don't have to think about how to actually do the reflection. Blender will give it to you with the reflect option in here. And it literally just, if you have, this is your hit normal. If you have a vector coming in like this, it will give you the vector coming out like this. That's all there is to it. So perfect for what we want. Perfect for collisions. Now, what about the ray direction? Because it definitely can't be straight down because there's nothing underneath us. It needs to be in the direction of either travel or the nearest collider. So we have to pick between that. And the reason that we're picking between that is because if you just go in the direction of travel, and let's say, yeah, let me do this. So if we're only interested in this direction and we're coming in at a gracing angle, this point doesn't think it's collided because this is not on the surface. However, we have clearly collided already. So what we actually need to do is just use the nearest surface point. So we're going to take our collider, find with the geometry proximity the nearest position on the face. Then, to find out the direction from where we are to where that position is, we subtract from this surface position our current position, and this is the ray direction. The ray length is going to be the radius of the ball, because if the ball can only see to its surface, then we only know when we have collided. So that's actually what we want. Just grab a radius node on there like this. If I tab back out, and rather than just taking the collider as the input, we're also going to mix in the bounds because I want to also bounce off the edge. So let's use a join geometry with the bounds on here as well. And now let's see if we bounce. Fuck, what did I forget? So something that I've done, which is a little bit silly, I actually need to make sure that this grid on our simulation input plugs all the way through to the grid on the simulation output. Remember what I said about things being loaded inside the loop? Well, on that second frame, because there was nothing connected, the grid disappeared. So we need to make sure that the grid goes through all the way every frame. So just make sure that's connected. Now if I press play, you can see that our ball is bouncing. How cool is that? Let's come in here. Let's grab another one of these reflect move. We're going to use the inverted. We're going to use another join geometry, taking again the inverted from the colliders. And I'm going to use another join geometry, join these two back together. And there we go. Now we have our balls bouncing within the space. Before we go any further, let's set up some visualization just to make sure that we can actually see what's going on. So we've got our points after the simulation loop. Let's grab an instance on points node with an icosphere, a couple of subdivision levels, and we'll set the scale based on the radius, which I know it's just 1 at the moment, but this is now going to be responsive to radius changes if you wanted to play with that. And we're going to set a material as well, just to give us a bit of color on here. Now we're going to material preview. Jump into your shader editor at the bottom. Let's grab a new material, call it balls. And I'm going to turn off my wireframe drawing on here. Let's get rid of this principal BSDF. Make sure we're assigning the balls material. And I will use the attribute IDX from the instancer. There we go. So because these are instances, I've not realized them, there's no point. We are going with the instancer for our shader attribute. And I'll just take the factor through a mix RGB. There we go. And let's go for an orange and a purple. Let's take our grid just directly through a set material, and I will join this with the balls as well. And we're going to make a new material, which will be called grid. There we go. And this time, rather than using IDX, I will use score in here from the geometry. And there we go, that looks pretty good. I might make my purple a bit darker. But there we have it. So this is looking good. We can now actually start thinking about how we want the score update to work. Which brings us on to the next part, which is updating the score. So let's move this down. We're going to take our grid run through here, underneath everything, and we need some bits of information. I need to be aware of when we've hit the surface and what we've hit on the surface. So we will be working on the grid to change information down here. So let's do Control G on that reboot. We've got grid in, grid out, but we're also going to have another input for our points because they're going to tell us what they've hit. So let's grab another geometry there. I'll just bring this up above. Let's tab back out. This node group is going to be called period update underscore score. Right click, show hide, node options. And I will just plug my points in here. Now, before we can actually do anything, we need to make sure that our points understand what they've hit. So let's come into our reflect move group, and we're going to be doing something with our raycast. Because when we hit the middle here, like if I come up here, at the point that I collide, I can read information off the collision surface. Now this collision surface can tell me the index that we stored for each one of those points. So if I use IDX attribute, which was an integer, and if I have a look at my collider, and I have a look at this named attribute, you can see that this is going 0 and then something else. If you ever want to just check that, you can use a white noise node. Let's just recreate that. So you can see they're all different, right? So they're all definitely different values. I can read the integer index when I've collided, and then I can read that back onto the grid. So let's take our store named attribute. We're going to take another one, and we're going to be storing the hit underscore index. This can be actually this is going to be a vector. So combine x, y, z. In the x component of our vector, we're going to be storing the attribute that we've just hit, or that we've just sampled from the surface there, that index. But we also want to know if we have hit this. Now, most of the time, I want this to be 0. So I'm not only going to update during a hit like I did with the move. This time we're going to read it constantly so that we can just only update during a hit on the grid, if that makes sense. So most of the time our balls will be bouncing around with a value of 0. In fact, we can have a look at them. Let's grab our points here and let's have a look at this. So obviously this one has just collided with the surface, but on the next frame we've got 0, 0. So it's only going to hit, it's only going to light up when it hits something, and that's what we're after. So now if we come back to our update score node, inside here, we can simply take our points. We will sample index. We're looking for the vector, which is a named attribute, hit index, hit underscore IDX. And if I look at the grid and I read this value, there we go. Just got that flash. There we go. So this is what we're interested in. This value here. If we separate x, y, z, we now know something, right? We have now this x value, which is, let's come to this point. So if I take a look at my grid, I take a look at this, we have 47 in x and 1 in y. So that 1 is hit. So that's good news. That 47 is the index of the cell that we've just hit. we can then find where the IDX attribute, which is essentially the face attribute, the face index, is equal to this. And this is the cell that we've just collided with. So now what we can do is we can use this to flip the score. It's going to go from a 0 to a 1 or a 1 to a 0. So on our grid, we want to store named attribute for the score. It's going to be a Boolean. And we just want to know the selection. We're only going to do this during a collision, so we'll take that off the y-axis there. And we want to know what the current score is with a named attribute. Score, there we go. And we're going to do also a not Boolean. So the not Boolean will just invert it. If I look at this, we have our score. If I look at this, we have the inverted score. Now the easiest way to set this up without needing to think about Boolean maths or anything like that is simply to use a switch node. Switching between two Booleans. And this is which cell to change, right? So this true value is going to be the one that is flipped. And you can see that there. This then becomes the new score. And it's that simple, kind of. Because this is clearly not happy. In fact, if we come into our... need to make sure this store named attribute is on the faces. There we go. So two things are happening that we don't like here. Number one, we have that bottom left-hand corner colliding, or sorry, turning value every time we collide with the outside. Because the outside walls, the boundary, does not have an index for the collision, which means that it's always going to just read as 0. We're not going to find out whether or not that's good information or not. So we need to make sure that we are also doing something in here to make sure that we know if we've collided with a boundary or a collider. So let's go and store another bit of information on the colliders. So back in our create collider node group, this one down here, we can simply, on our collider section, use a store named attribute. Call this one trigger. On the point domain, a Boolean, which I will turn on. So if I look for the named attribute trigger in here, you can see it's on. And if I look for it on my bounds, you can see it's off, right? So it only exists on the place that I've written it. So we can now use this trigger attribute in our reflect move when we sample the index. So we're going to sample the index and that trigger attribute. We're simply going to join these with a combine XYZ. And the raycast will be passing a vector instead of an integer. And there we go. So now we have a trigger attribute in the y-axis. Let's use a separate XYZ on the attribute coming through there. And we still have the same X value coming through. So that's our index. That's still true, right? So this is going to be the exact same behavior right now. The next thing that we want to do is make sure that it's only going to register a hit when it is a hit and when it is a trigger. So we're going to use a utility math, Boolean math node set to and with that y-axis. And that was our trigger attribute. And now you can see we don't change that bottom left-hand corner. We only collide with that middle section. Okay, but the orange ball doesn't seem to get a look in. So what are we going to do about that? Well, let's go back to our update score in here. And it's because we're only dealing with index 0. If I change this to index 1, you'll see that now the orange ball gets it. Well, let's look at how we can mess around with repeat zones to pretend we have a for each working because geometry nodes will be getting a for each loop, which is where it will go through each kind of like separate group, if you want, of elements. In this case, for example, we would use the index. We would say for the first point, do this operation, and then for the second point, do this operation. For each is going to be more optimal because it will do it in parallel. The repeat zone, which is under utilities, repeat zone, this will do it in series. So it's a little bit slower, but saves us duplicating all of these nodes. And really, a system this easy is not going to be heavy at all. So let's throw all of this into a repeat zone. And to begin with, take your repeat zone, go to your node tab, add a new input here called loop IDX, loop index, move it to the top, make it into an integer, and then we're going to add with a math node 1, which we will just pass straight out there. So this is just adding 1 each loop. So this is how you can sort of hack a loop out of our repeat zones. We're going to be passing in the grid and the points. So let's rename our geometry to points, just so that we know what's what. And we will pass the grid straight through, so not having that problem that we had earlier with the simulation loop. Now, take your grid, and this will go into that store named attribute node. And the loop index is going to go into your sample index node. The grid is going to come up here. And we're going to just pass out the grid on the far end. So all of the same data that we did, but it's going to go through this loop first. Now, if I play, nothing has changed because our loop iterations is 1. Now you can just set this to 2, and then you can see that they're actually battling now. So this is working correctly. Another thing that you might want to know to do is to use something like a domain size node with the point cloud. So I know my points are coming in. How many points do we have? We have 2 of them. That's how many iterations we're going to do. And then we're looping over and separating out each point. It's essentially doing a for each loop. So if you're familiar with for each loops, this is now doing that. And that's it. That's the game. It's now working. So you can now play around with this as much as you want. We'll actually do a little score readout because I think that might be fun to play with. If you ever want to change the speed of these or the radius, let's set them up to 2 meter radius, you will need to just go back to the start to have that updated. You can always change the number of points as well. So let's go to 21 points for a 20 by 20 grid. Now it's going to play a little slower. Okay, let's do the quick score thing and then we will wrap it up. All we want to do here is have a simple number readout under each side for how many tiles is owned by each side. Let's take our grid, separate the geometry by the named attribute score. And there you go. Now we have the left and the right side. We can use a domain size node on the mesh to see how many faces we have. Do Control H to collapse that, and then I'll move down. Oh, something I just did wrong there. The points should be faces. There we go. That makes sense. If you separate by points, you'll get a face dropped. So there we go. That was my bad. Separate geometry by faces on the score attribute, and now we can count what that is. We will simply put our face count through a value to string node. This is only possible because the domain size passes out a circle socket, which means it's a constant. It's not different per mesh element, like you can see a diamond socket can support. So if you ever want to use the value to string, you either need to use domain size or something like attribute statistics, which will also pass out flat values. So domain size is what we're after here. Value to string through a curve, string to curve nodes. Let's have a look at this. A little bit small, let's go up to 5 meters. And let's also do a fill curve on here. We're going to center it. We're going to put it to the top is going to be what it's hanging underneath. And that's just going to make it easier for us to do a transform to move it into position, which is going to be left 10, so minus 10, and then minus 20, just so it appears underneath that 40 by 40 grid that we have. Same thing is going to happen on this lower section, except this one is going to go to the positive 10, and then we can simply join these two together, and I will also just join them up to the outside there. We want them to get materials as well, so we'll just throw on a grid material that's coming through orange. So we also need to do a store named attribute. I'm just going to make one side have the score turned on because that's our Boolean. Make sure that we're doing this on points. We're going to need to realize instances for both of these, storing our score on the face domain for one of these. There we have it. That was a little bit of a quick tour through using simulation nodes, creating this kind of fun effect. I really enjoy watching it. It's very hypnotic, especially when you have the numbers to keep track of who's winning. I feel like it shouldn't be so fun. I would recommend now, if you want to kind of escalate this further, is go ahead and find a way of making it three-dimensional. This is obviously just a 2D grid, but there's no reason that you can't use pretty much the same logic to bounce around a 3D grid of points. And it'll just make a little bit more interesting viewing, perhaps, how they burrow into each other. But there we go. This is that game that you've been seeing popping up on Twitter. Hope you enjoyed it. Hope you learned something. I'll catch you in the next one.